In this video, we're going to talk about the unit circle. Before we start talking about the unit circle, let's first of all review some of our basic trigonometry rules. So we have 6 key trigonometric functions that we will consistently need to use. The first one that we should all be well aware of is our sine function, which is spelled S-I-N-E, but is abbreviated as sin, but don't say sin, say sine. So we have a function sine x, right? And we also have cosine, and we also have tangent. And as we know from way back when, these are relations of specific ratios of a right triangle. So just so you can visualize this, down here we have a right triangle. And imagine that it is a perfect right triangle, because some of my drawings are not the best. So we need to have an angle somewhere in this triangle that we are referring to, otherwise we don't know which sine, cosine, and tangent that we're talking about. So I'm going to put our theta, our degree measure, or radian measure, down here at the bottom. And we have some corresponding values that we need to know of. So the side that is directly opposite of our theta, imagine shooting a bow and arrow through this arc right here, and that is our opposite side. Okay? We know where the hypotenuse is because it's always the side that's opposite the right angle. So we look for this side here, that is our hypotenuse, and the one that's left over is the adjacent side. It's the side that's next to or touching our theta. That's not the hypotenuse. So let's go back up to our trig functions. Sine's relationship in this particular triangle is the opposite side over the hypotenuse side. And our cosine is the adjacent side over the hypotenuse side. And our tangent is the opposite over adjacent. And there's a very simple way of remembering this. I'm sure a lot of you have already seen this. To remember sine, we do S-O-H, which gives us so. We also have cosine, which is C-A-H, so ka. And then we have tangent, T-O-A, which is toa. So this is all combined to say SOHCAHTOA. And that's just a really nice phonetic way of remembering those ratios. So these guys also have what are called reciprocal functions. And as you know, a reciprocal is when a fraction or a ratio is flipped. The numerator becomes the denominator, and the denominator becomes the numerator. So sine's reciprocal function is called cosecant, which is abbreviated as CSC. So if cosecant is the reciprocal of sine, then we would flip this, and instead of opposite over hypotenuse, we would have hypotenuse over opposite. So the same exact thing goes for cosine. Cosine's reciprocal name is just secant, which is abbreviated as SEC, and we flip cosine's ratio. So instead of adjacent over hypotenuse, it becomes hypotenuse over adjacent. And then last but not least, we have tangent, and his reciprocal function is cotangent, which is abbreviated as COT, and is the reciprocal of tangent, which would be adjacent over opposite. So those are the key 6 trig functions that we will consistently be working with. Keep these in mind. If you want to also have a phonetic way of understanding the reciprocals, we can do that real quick as well. This is not well known at all. However, we can still do C, H, O, which would give us show. We have S-H-A, Shaw. And then we have C-A-O, cow, which actually in Japanese, this right here means face. So that's a little fun fact for you. So we have so, katoa, and cho, sha, cow. Okay, so now that we know this, we want to review another key concept before moving on to the unit circle, which are our special right triangles. We have 3 of them, so let's review those real quick. Our first one is one that looks like this. We have a right angle here, and we have an angle measure here in radians or degrees. And this is a 30, 60, 90 triangle. And the ratios of the sides of a triangle with these angle measures are always going to be the same. And the ratio is that the small leg, the one that's vertical, is a length of 1. The hypotenuse will always be double the size of your small leg. And the adjacent side here down at the bottom will always have a value of root 3. So no matter what your sides are, you can always find the ratio of them. For example, let's say I asked you for the sine of theta. Okay, so again, we want to locate our theta first, which is all the way down here. Okay, we know that sine has a ratio of opposite over hypotenuse. So I would take the opposite value, again, shoot a bow and arrow through your arc here, and you would get 1. And then we would put that over the hypotenuse, which has a length of 2. So regardless of if this one is a 5, and this is a 10, and this one is 1 times the square root of 3, which is just square root of 3. That one's not going to change. But you need to multiply it by whatever this is. Okay? This long side, this root 3, is always multiplied by the small side no matter what. So I don't just get the root 3, I have 5 root 3. Okay? I'm going to do that again with another pair of values. So let's say that this side is 4. How big would this side be? If it would be 8, right? Because it's double the short side. Now this one. See if you can figure it out before I write the answer down. Okay, so to get this side, you take the small side, which is 4, and you multiply it by root 3. So 4 root 3. These ratios are consistent in every single right triangle that has a 30, 60, 90 degree measure. So this is a really key right triangle to remember. Let's move on to the next one. And the next one looks something like this. Okay, this is going to be a 45, 45, 90 degree triangle. And the special ratios for this particular triangle is that since these angles are the same, they are congruent, it means that their sides are going to be the same as well. So they have a ratio of 1 to 1. The hypotenuse in this case is root 2. Is this true for every single 45, 45, 90 triangle? Yes, it is. No matter what the lengths are, they will always have this relationship. So real quick, let's say I asked you, what is the cosine of theta? So we would grab the adjacent side and put that over the hypotenuse side. That is the relationship of cosine. So in case you're ever unsure of where the adjacent side is, remember that adjacent means next to, but not the hypotenuse. Otherwise, it would be the hypotenuse. So the only one that we're left with is this guy, the 1. So we're going to write 1 over, and then the hypotenuse, which is root 2. Now, this gives us a very interesting situation, because in mathematics, it is very informal and improper to have a square root or any root in the denominator. There's a special process called rationalization that gets rid of the radical in the denominator and moves it to the numerator. And I'm going to show you the process on how to do that real quick. So let's take our ratio, 1 over root 2, and all you need to simply do is to multiply it by the root you don't want in the denominator anymore, which in this case is root 2. And whatever you do to the numerator, you must also do to the denominator. So we're going to simplify this. And when you multiply fractions, it's top to top, bottom to bottom. 1 times square root of 2 is just square root of 2. Square root of 2 times square root of 2 is square root of 4, which is equal to 2. And here's a quick trick. For those of you that may not know this yet, whenever you multiply a radical by itself, you will always end up with the number that was inside. For example, if I had root 3 times root 3, I would just have 3. If I had root 15 times root 15, my answer would just be 15. Okay? So let's take a look at our last triangle. And this is a terrible drawing, I'm sorry, but it's the best I can do. So this is actually the same exact thing as our first triangle, but its orientation has switched. And this is really important to go over because on the unit circle, what we're about to go into uses this orientation a lot, just like the other two. So I just want to make sure that we go over it. So the larger angle this time is down here at the bottom. This is a 60, up here is a 30, and here's a 90. So it's going to have the same exact ratios as our first triangle, just in different places. Okay? So in this case, we are going to have our short side just like over here as a ratio of 1. Our short side in this green triangle is down here at the bottom, so this is 1. It looks like this is going to be a Green Bay Packer triangle. All right, our hypotenuse, just like the original, was 2. So our hypotenuse over here is also 2. And the adjacent side is root 3. So let's quickly do an example, make sure that we understand our trig functions as well. We're going to find the tangent of theta here. So again, let's remember our tangent ratio. It's opposite over hypotenuse. So we need the opposite side. Make your bow and arrow through theta. There we go, root 3. And the adjacent side is just 1. This can be simplified to just root 3. This particular ratio does not need to be rationalized because the square root is not in the denominator. So now that we have our basic knowledge, we're going to move into the unit circle. All right, we finally made it. So this is going to take just a little bit to understand. Not understand, but to do. So please be patient. We're going to pull all of our previous knowledge into this circle. This is a famous, well-known, useful circle that has many, many incredibly consistent special relationships that you will use in your entire course for trigonometry. So here's our circle on an XY grid. This is our x-axis. This is our y-axis. And we also know that there are 4 quadrants, right? We have the first, the second, the third, and the fourth. So when we talk about the unit circle, we're talking about all these trig values. So what we do is we actually make everything refer back to them. Instead of our x-axis being represented by an x, in the unit circle, all of the x values in a coordinate, for example, like this, xy, is actually instead cosine, sine. So all of the x values that you're going to see in every coordinate represent a cosine value from these right triangles. And all of the y values that you see are going to be sine values, all the sine values that we got on the previous screen as well. So what we're going to do is we are going to rename our axes so that they fit the trig that we're about to use. So we're going to name our x-axis cosine, and our y-axis as sine. Okay? So the first thing that we need to do is see how these special right triangles play a part in this. We also know and need to know that in the unit circle, we are dealing with a radius of 1 unit, always, okay? It could be 1 inch, 1 foot, 1 meter, 1 centimeter, however big that you want it to be, but it must be 1 unit of that measurement, okay? If that radius changes, this unit circle doesn't work anymore. So it must have a radius of 1. So we're going to, first of all, go with our smallest special right triangle, which had the 30 degrees where theta is. So I'm going to start by trying to draw that particular triangle in the first quadrant. And here's how we do that. We're going to center the origin, okay? The base of the triangle is going to lie along the cosine axis, the x-axis, okay? And then we are going to, in this case, I'm estimating, but it's going to be a pretty small angle. Up here we have 90 degrees, and here we have 0 degrees, as we've already seen. So 30 degrees would be about a third of the way up to 90. So I'm going to estimate that to be about here. And I'm going to connect that to the origin to make my angle. This is a 30-degree angle here, okay? And we are going to, in order to make that right triangle, we take the intersection on the circle and we drop it down to the x or cosine axis. That's how we get our right angles. This is always going to be the same exact process, okay? So, in this particular triangle, if this is a 30, 60, 90, I already know the ratios that I need to work with. The small leg over here is 1, our hypotenuse is 2, and our long leg is root 3. Okay, so in order to get a coordinate out of this point right here, we are first of all going to have to get the cosine value of that triangle and the sine value, and then we'll have our first trigonometric unit circle coordinate. So here we go. Let me erase that, and we're going to work this out slowly so that it makes a lot of sense. Cosine, in order from this angle, is adjacent over hypotenuse. Here's the adjacent, here's the hypotenuse, so it's going to be root 3 over 2. And of course, you need to make sure that if you have a root in a fraction, make sure if it needs to be rationalized or not. This does not, because the radical is in the numerator. Next, we need to get the sine. This guy right here. We are onto the y value. So sine is opposite over hypotenuse. In this case, that's going to be 1 over 2. So there we go. That is the first coordinate on our unit circle. Now, this specific right triangle occurs in all 4 quadrants. So we're going to take a look at what these values are everywhere. Okay? So when we transform that into the second quadrant, we simply reflect it across the y or the sine axis. So I'm going to flip it as if this were a mirror, okay? And that's going to give us, this is my new base. And again, I'm going to go a third of the way up the second quadrant, which would be about here. And we are going to connect that to the origin to get our right triangle, find that third of the way up point, and drop it down to the horizontal axis. There we have our right angle. Okay, so same thing, our theta is always going to be at the origin, no matter what. We still have the same ratios of 1 to root 3. Okay, however, we are not going to get the exact same answers as the first quadrant. And the reason is because in our parent graph, in our Cartesian coordinate system that you have been working with forever, we have positive x's over here, positive y's up here, negative x's here, negative y's here. So in the first quadrant, when I have anything in here, my answers are always going to be a positive and a positive, no matter what. Every trig function in the first quadrant is positive, no exceptions. However, when we get to the second quadrant, we have to be careful. Now remember, in our coordinates, we have cosine for the x, which in this case would be negative, and we have sine as the y values, which in this case will be positive. So our coordinate is going to be very similar to the one we got in the first quadrant, this one right here, okay? However, we need to watch the signs. So let's go ahead and get this started. If you want to make the negatives in your right triangle first, that's absolutely fine. Since this right here is our y-axis part of our triangle, it's a positive value. So this 1 is a positive 1, okay? However, as soon as we get to the horizontal part, that's on the x-axis, and the x-axis in the second quadrant is negative. So I'm just going to go up to that root 3 and make it negative. Don't ever worry about the hypotenuse having weird signs. Hypotenuses are always positive because of the Pythagorean theorem. So, here we go. Let's make our cosine value. Cosine, again, from theta is adjacent over hypotenuse. So again, it's still root 3, but negative over 2. So negative root 3 over 2. And our sine value is opposite over hypotenuse, which is still positive 1/2. So as you can see, the coordinates are incredibly similar. You did this, just the signs are switched. Okay, so now we're going to move on into the third quadrant. To move this particular right triangle into the third quadrant, we're going to reflect it about the x-axis this time from the second quadrant. So the x-axis is still my base. However, instead of going a third of the way up the third quadrant like here, we're going to go a third of the way down. So about here. Same process. Connect it to the center. Drop it to the x-axis, and these should be perfectly right on top of each other, okay, if this is done exactly. Here is our theta centered at the origin, and our ratios 1 to square root of 3. So let's go ahead and figure out what signs we need first. So let's look back down here at the bottom left of the screen where we have our Cartesian coordinate system. If we're in the third quadrant, that's supposed to be an arrow. That was bad. Sorry. There we go. We're going to have a cosine value, an x value, that is still negative. And this time our sine value, if it's down here, is also negative. So in my picture, I'm going to make both the vertical side, which is the 1, negative, and the horizontal side also negative. Again, do not touch the hypotenuse. So we get our coordinate on here, and we start figuring out our sine and cosine values. Cosine is going to be adjacent over hypotenuse. So again, we have negative root 3 over 2. And then our sine value, which is opposite over opposite over hypotenuse, so negative 1 over 2, or negative 1/2. And now we're going to do the same exact thing, but in the fourth quadrant. So here we go. I'm just going to rewrite that root 3 that was there because it was in my way. So again, we're going to make it look exactly reflected. We are going to go about a third of the way down, connect it to the origin, connect that point to the x-axis. It almost looks like a bow tie if you're looking at all 4 quadrants. Again, here's theta at the origin. My small side is 1. My hypotenuse is 2. My horizontal side is root 3. And let's figure out the signs for a fourth quadrant real quick. So down here, our cosine value, our x value, is going to be positive, so we're going to leave this root 3 right here alone. We are not going to make it negative. However, sine is still negative in the fourth quadrant. So I'm going to find the vertical side, which is 1, and make it negative. And now we're ready to rock and roll. So we get our coordinates set up, and we do our cosine value adjacent over hypotenuse. That's going to be root 3 over 2. And then we're going to do our sine, which is opposite over hypotenuse, negative 1 half. So notice all four coordinates are incredibly similar, but the signs make a difference. It will tell you which quadrant that you're in. So what we can determine at this particular point in time, this is also something key to remember, is sine is positive in the first quadrant, so is cosine. In the second quadrant, sine is positive, cosine is negative. In the third quadrant, sine is negative, cosine is negative. And in the fourth quadrant, sine is still negative, but the cosine is positive. This is true every single time. So we're going to do this process a little bit quicker with the other two right triangles. Keep it all on the same circle if you can. If your circle is looking as busy as mine is, you might want to draw a new one, which I'm about to do, so you can read everything really clearly. All right, so the next triangle that we're going to use is the 45, 45, 90 triangle. So again, we are going to make the horizontal axis our base. 45 degrees on the first quadrant is halfway up to 90, so about here. So connect it and drop it down, and there's our right triangle. And where should theta be? It should not be on the circle, it should be at the origin, right down here. The ratios for a 45, 45, 90 triangle are 1, 1, and root 2. Again, these ratios only work if the radius is 1. We are going to get our sine and cosine values in here. And again, remember that both sine and cosine are positive in the first quadrant. So cosine, adjacent over hypotenuse, that's going to be 1 over the square root of 2, which of course is an issue, because we have a radical in the denominator. We saw just a minute ago that when we rationalize this, we actually get root 2 over 2. So I'm going to use that previous knowledge to make this a little bit quicker. And then we need to do the sine value, which is opposite over hypotenuse. Notice we're going to get the exact same thing that we just got for cosine. Well, again, if it's the same thing and I have to rationalize this, it's going to be still square root of 2 over 2. So we're going to get rid of that and rewrite it thusly. All right, and this is at 45 degrees. I did not do this for the previous circle, but we'll go back and fill that in. All right, so we're going to reflect this into the second quadrant. And remember, in the second quadrant, our cosine values are negative, our sine values are positive. So we are going to make this our base, go halfway up the circle, connect it to the origin, and drop it down. There's my right angle, there's theta. I put in my ratios, 1, 1, root 2, and we get down to business. So this coordinate right here has cosine as, again, adjacent over hypotenuse, which is going to be root 2 over 2 again. So the only thing I'm going to do differently is make it negative, because that's how cosine works, or x's work in the second quadrant, and our sine value is going to be the exact same thing, but positive. This is the really nice thing about the 45, 45, 90 triangles, is the sine and cosine values are pretty much identical. All right, down to the third quadrant. We are going to go halfway down, connect it, and drop it. Right angle, theta, 1, 1, root 2. And in the third quadrant, my cosine values are negative, and so are my sine values. So we're going to get our coordinate on here for this point. which is going to be negative root 2 over 2 and negative root 2 over 2. We're going to do this again in the fourth quadrant. Again, it should look like a bow tie if you're reflecting these correctly. We're going to go halfway down the triangle, connect it to the origin, and drop it down. Okay, still same thing, 1, 1, root 2, theta is at the origin. And in the fourth quadrant, we have positive cosines, negative sines. So our coordinate for this point right here is going to be positive root 2 over 2 and negative root 2 over 2. So that's our 45 degrees. Now the reason why I put this 45 degrees in here is because this theta right here is not 45 degrees. It's built off of a 45, 90 triangle, but that's not where it is on the entire circle. To figure out where this is, okay, remember that in order to gain a degree measure, you have to start the initial side on the unit circle at the x-axis, the positive x-axis. So this point that I already found up here needs to connect to the origin, which we already did. So the total measure is going to be whatever the degree measure is from here to here. We know that this first quadrant makes up 90 degrees, and we need to add 45 more degrees, which is going to give us a measure of 135 degrees. You'll see a spot for this on your unit circle. That's where this is located. So let's find out the degree measure for the third quadrant. So again, we need to do a full 180, because this is 180 degrees over here, plus another 45, which would give us 225 degrees. So this coordinate happens at 225. And of course, the last one, what we could simply do, this is 360 degrees over here. If you wanted to add all of them up again, you're perfectly welcome to. However, you can just do 360 minus 45, which is 315. So these are the special measures for the 45, 90 triangles around your circle. I'm going to backtrack real quick so we can do that with this one. And I know that there's a lot going on in this picture already, but try to keep up, try to follow along as the best that you can. Okay, so I'm trying to find a color that's going to stand out. We're going to do a bright green. So this one right here, of course, our first coordinate is at 30 degrees because that's where we started. We now need to get to this point over here. Okay, again, it's going to be our first quadrant, which was 90 degrees, plus however much this is. Okay, it's not 30 degrees because this measure right here is that 30. So this must be 60 degrees up here to make up another 90. So I'm going to do 90 plus this 60, which gives us 150 degrees. That is your coordinate for 150. Now, to get the next one, we're going to do the full 180 degrees, our semicircle up on top, plus 30 more, which is going to give us 210 degrees. And then our last one, instead of adding everything up together, we can do 360 minus 30, which gives us 330 degrees. Okay, we've got one more special right triangle case to go, and then we're done. So, I've already set up our 60, 30, 90 triangles. And of course, if you'd like to pause this video at this time to copy the picture, please do so before I move on. So, we're going to rock and roll this. We have the same ratios, except our short side is now the base of this. So this is our 1, this is our 2, this is our root 3, which means our coordinate here at 60 degrees is going to be, for cosine, adjacent over hypotenuse, which is 1/2. And our sine is going to be root 3 over 2. Nothing needs to be rationalized. This is happening at 60 degrees Let's move on to the second quadrant. Again, we've got 1, 2, root 3. This degree measure here is going to be 90 degrees plus this much. Remember that this from here to here is what the 60 degrees is representing, which means this must be 30. So 90 and 30 is 120. The coordinate for that, and I'm sorry I don't have enough space at the top, I'm just going to do this over here, is going to be the same exact values as the first quadrant, but with different signs. So the 1/2 that we got is now negative, and our root 3 over 2 is still the same. So now we need to figure out where this degree measure is in the third quadrant. This over here is 180, and we need to add 60 more, which is going to be 240. And the coordinate is the same as the first quadrant, but we need to change both of the signs, negative 1/2, negative root 3 over 2. And last but not least, we're going to get this guy here. This is 360. We're going to subtract the 60 degrees, which gives us 300 degrees. And the coordinate, again, same as the first quadrant, but our sign is going to be negative. So once you have all of this on a unit circle, it will look something like this. And it's pretty cool. So here's all the coordinates that we got from those special right triangles. These are the degree measures that they happen at, right? And these guys right here are their radian equivalents. Okay, of course you can always just multiply these degree measures by pi over 180 degrees and simplify, and you will get these pi over 3, pi over 4 values. These are also going to be things that you're going to need to know by heart. I just want to go over one small thing before we close, and that is these coordinates right here. This is at 0 or 360 degrees, right, which is also here. We've got this one up here, and this one here, and this one here. These are special because, again, if this length is 1, that means that the x value here is 1 and the y value is 0. That's why the cosine is 1 and this is 0. That's how we get that coordinate. Up here up top, this again is 1, but that's now the y value, and it's happening at an x value of 0. So that's how they got that. And so on and so forth all the way around. And note that the signs are still consistent with which quadrant that they are in. You have to watch that. So that wraps up the unit circle, and thank you for watching this tutorial.